Ken is a software developer in the Intel's HPC organization in Cloud and Enterprise Solutions Group. He is contributing to the development of the Distributed Asynchronous Object Storage, in other words, DAOS. It is a very large-scale distributed software storage solution. His experience in high-performance networking includes switch and fabric management software, high-performance host interfaces, and communication middleware. It spans HPC, traditional Ethernet, and also embedded systems interconnects. So it's my pleasure to welcome Cain to the presentation. It is up. Ken, I think you're unmuted already. Go ahead, give it a try.
Okay, thank you very much, Divya. I'm very happy to be able to contribute to the OFA workshop this year. Today I'm joined by my colleagues at Intel, Johan Lombardi. He's a senior principal engineer and the lead architect of DAOS, and Alex Oganizov, software developer also for DAOS. Can we go next 2 slides? Thanks. So the objectives for the presentation today are to share architectural level information on DAOS, to share some lessons learned in implementing DAOS to run on clusters that are connected with high performance fabrics and using OFI and LIBFABRIC as the software interface vehicle for communications. And finally, in a spirit of brainstorming and collaboration, to consider opportunities where DAOS might be able to take advantage of additional fabric or network features. And we'll present just a few thoughts in that category. Can we go ahead by 2 again? So for the DAOS architecture, we're going to start with this figure on the right-hand side and cover it over the next 2 or 3 slides. We'll go top to bottom. So in a typical data center or an enterprise cluster, we expect a large number of compute nodes that could be running many simultaneous scaled out applications. There could be various types of workloads like HPC simulations, AI, or data analytics. The workloads could use different middlewares or software interfaces to storage. And so the figure at the top left we'll get to in a moment. We'll kind of cover that a little bit. In the middle of the figure, we have a scalable high-performance interconnect that serves application to application and application to storage communications. And at the bottom, we have smaller, likely a smaller set of nodes, but still potentially very significant number of servers that are dedicated to providing collectively a large amount of distributed storage capacity for the applications to use. And these nodes would run just the DAOS storage service, no applications. So going back to the client interfaces at the top left, some of these interfaces have been developed to interface with DAOS and its library architecture that provides access to the storage service. And some of them are under investigation, and the color coding shows which interfaces have been or are in development right now. On the slide, we have a few examples listed. So accessing a POSIX namespace that's hosted on the DAOS storage system, directory and file access. In the clients, if they want to access this through user space, there are a couple of options. One is to directly call a POSIX-like, but DAOS-specific API called LIBFABRIC for directories and files. Another option is to link with a POSIX API interception library so that the read and write calls would go through user space to DAOS storage. And for traditional file system access, we do have a fuse daemon option, but that would be going through the kernel. For applications that use MPI-I, there is an ADIO driver in MPICH. This layers over a distributed array library in DAOS. And for applications that wish to use a key value store interface, the DAOS API is exposed with Python bindings and offering some integration with Python dictionaries. Next slide, please. So here we'll focus on the communications between the applications and storage. So the focus here is on those fabrics that provide OS bypass, user space communication services that allow the opportunity to interact directly with application memory. So the client to DAOS server interaction is a combination of 2 things. It's a remote procedure call that the client initiates. This is done with tagged messages in LIBFABRIC. And then the ensuing bulk data transfer that's initiated on the server side. And this is done with read message and write message in LIBFABRIC, so RDMA messages. So if the client were writing I/O into the DAOS storage service, then on the server side, this would turn into an RDMA read to pull the data from the client memory into the server memory. So in the servers themselves, we can see that there's two types of media. There's data center persistent memory and solid state drives. The next slide, we'll talk a little bit about how the media selection is made on the server. But first, let's just consider how data would arrive over the fabric and land in either one of those devices. So again, with the example of client writing data, then this would require, again, the server to initiate an RDMA read. So regarding the persistent memory, in the server, it's memory mapped with the PMDK, or Persistent Memory Development Kit software. So this destination persistent memory can be the target of an RDMA read. And persistent memory does offer non-volatile qualities, but it requires a transactional interaction with the device. The important part here is that the DAOS server doesn't require the RDMA stack to provide that consistency semantic. Instead, it waits for the RDMA to complete and then uses PMDK to transact the information into the device. And then regarding landing data in the SSD drives, the server, in this case, will provide its own DRAM buffer as the destination of the RDMA read. And then we'll use the SPDK, or Storage Performance Development Kit, to get the data into the device. Okay, next slide, please. So in terms of how the data arrives in either persistent memory or SSD, there are actually two levels of data placement in DAOS. So if we start with an example, let's say the client is inserting a key value into a distributed KV store. DAOS has a first level of data placement where the client library will algorithmically decide, based on the key and the object class, the server or potentially multiple servers where the data will be stored. I say servers in plural because DAOS has some data protection features such as replication or erasure code, so that multiple servers could be involved in storing the data or computed parity for objects. This first level of placement is also fault domain aware, so the architecture of DAOS is intended to allow for hierarchical representations of the DAOS servers so that, for example, if there are a collection of servers in a common rack, then that could be considered a fault domain. So the data placement objective here would be to take any replicated data and place them on servers that are very far apart so that data availability can be maintained if an entire fault domain goes away at once. The second level of placement is on the server itself to make that media selection. So small IOs, which are potentially unaligned, byte granular, are going to land in the persistent memory. That'll be much more efficient to access than SSD. Large application blocks of data, and really application-only data is going to be stored in the SSDs for high storage throughput. And finally, any DAOS metadata, so any indexing structures, will be maintained entirely in persistent memory. And one important quality of the implementation is within the server over time, you could have small IOs that may have landed in persistent memory, collected and packaged up and migrated to the SSDs to preserve space in persistent memory. Okay. Let's move to the next slide, please. So here we're going to talk about some common properties of those data protection features I mentioned, replication and erasure code. So this involves storing either whole copies of objects or the computed parity on different servers, so we can have that enhanced data availability in the event of a failure. But before we consider a failure case, how does this work before the failure? The I/O that happens between the client and the servers is done directly, and that's shown by the large fat arrows in the figure. So for example, with replication, the client is going to deliver the copies of the data to the multiple storage servers involved. Meanwhile, on the server side, the multiple servers do implement a distributed transaction protocol, and that's shown by the thin blue arrows in the figure. And this is driven, initiated from a designated leader server to the other servers involved. And the very important quality of this is that there is no single leader server in DAOS. The leader is chosen based on the object's key. So another way to look at this is that every server in DAOS could be the leader for some portion of the key space. So there are a lot of details to the distributed transaction protocol, but for example, if the client is trying to read data that's replicated, it could send the I/O request to any of the servers, and the distributed transaction protocol on the server side will govern whether or not a non-leader server is able to serve the read for a particular version of the object. So when there is a failure, DAOS will go into a so-called degraded mode, which basically refers to the ability for the servers to continue to serve client I/O even though the original degree of data protection has been reduced due to the server failure. In parallel to this and in the background, we have a self-healing and rebuild capability that will happen with the goal to restore that original data protection level. So the rebuild here is so-called declustered, which means, for example, if we had a server loss and there were 10 objects whose redundancy levels were impacted by that loss, then when an additional replacement server is identified, not all of the data movement is going to go to that single server. All of the servers in the pool will be recruited to help store some of the data as we restore that redundancy level. And another important property of this online self-healing rebuild is that it's throttled compared to the ongoing client I/O, which is obviously a top priority to keep serving. So we want to limit the impact of this rebuild process on actual I/O. Okay, next slide. So we're going to switch gears now and take a look at how DAOS engages OFI LIBFABRIC. So here we have DAOS at the top of this software stack, and then DAOS has its own integrated remote procedure call library called CART. And this engages OFI LIBFABRIC indirectly through another RPC library called Mercury. So DAOS is depending essentially on Mercury and OFI as externally developed components by other groups in the industry. But the DAOS team does occasionally contribute changes to Mercury and OFI down the stack as necessary. What the CART layer is adding upon Mercury here is, generally speaking, reliability mechanisms and some convenient abstractions and mechanisms for multi-node communication. So for now, on this slide, let's focus on the item that talks about the SWIM protocol and on the collectives. So DAOS is going to operate in an inherently dynamic environment. So the set of servers that are functioning in the service may contract or expand due to unexpected faults, or it could even be due to some administrative action. For example, adding more servers into the system to expand overall capacity. So DAOS really needs to detect when a server node appears to no longer be reachable. So this SWIM protocol is a gossip-like protocol implemented in CART that provides the capability for DAOS. So in reaction to those kind of events, DAOS will use collective communication mechanisms across whole groups of servers to trigger, the subsequent reaction. For example, if we do have a fault that results in the loss of a server, then there's a so-called pool map update, which is done through collective communication so that all of the nodes in the storage pool can take action, for example, to participate in a rebuild or self-healing process. Okay, next slide. So here this just talks a little bit about how CART is using multiple communication contexts within one server. So when RPCs are directed at a DAOS server, there are two levels of addressing, like MPI. Here, every DAOS server is given a numeric rank to identify it within the system. And then because multiple communication contexts or tags, sort of like a port model, are used within the server, then that is also a component of the destination address. So the multiple contexts are used to separate different types of RPC request processing. There is a context 0 that's used for administrative work like metadata RPC requests and also to implement that SWIM protocol that we talked about. The other contexts are pretty much related to I/O activity on so-called storage targets. So a DAOS server by configuration is organized into some number of targets that's roughly related to the number of CPU cores in the server and the number of SSDs installed in the machine. And then from the DAOS perspective, it uses a multiple threading model. It has so-called execution streams, which are pthreads, roughly associated with the number of targets. There is a special thread that's used for that metadata and SWIM processing on the context 0. And then there's a thread per storage target. And optionally, there can be some additional helper threads potentially configured, per target as well to support, for example, some of those background activities like the rebuild. Furthermore, within a given pthread, there is user-level threading that's being done using the Argobots library to minimize the context switching overhead for activities that are running on that within that thread. Okay, next slide, please. Okay, so this slide is about point-to-point RPCs in CART. We're going to skip reading through each of these and maybe just focus on the bottom one, which is the progress model in CART. So nothing really happens in CART until the progress function called CRT progress is invoked. This CART progress could be invoked in the same thread that's making other API calls, such as constructing an RPC message or sending it, or it could be invoked in a continuous loop in some separate progress thread. It's up to the caller. And CART is a callback function-based library, so the CART user, DAOS in this case, is going to provide functions to handle incoming RPCs, for example, to handle any replies to those RPC messages, to perform processing upon completion of bulk data transfers, and so on. Again, all of these callbacks are going to be invoked in the context of that progress function. Next slide, please. Okay, so this is taking a look at the collective communication support in CART. So similar to MPI, CART has scalable multi-node collectives, some familiar examples like barrier sync and broadcast. These are implemented through spanning tree style propagation and replies. A simple example of DAOS using a broadcast would be if a client contacts the storage service and asks for storage to be provisioned, a so-called storage pool create, then a leader of this storage pool will be established, and that will become the root of a broadcast to all of the other servers that are going to be providing persistent memory or solid state disk space for this pool. So that broadcast is needed to trigger those servers to take some action, such as their local allocation and other setup activities, so that the pool can become operational. Another feature is called incast variable, which is a little bit complex, but it represents a scalable way for many-to-one shared access to a common piece of data or a variable. One node is the root of the tree for this variable, and the goal is that any of the given nodes can do a quick lookup of the variable's value, presuming that it has a valid version of that variable. And there are mechanisms using collective tree-based communication to invalidate the variable or update its value. One example of that I mentioned before was the pool map update that happens in reaction to a server appearing to no longer be reachable over the fabric. Okay, let's go next by 2 slides, I guess. So now we're going to transition into lessons learned implementing DAOS over LIBFABRIC. So the main, this is the most important slide in this section, basically that DAOS is a client-server model versus an MPI model. So in a client-server environment, the client and the server life cycles are different. They're decoupled. The DAOS service as a collection is going to run on an almost permanent basis. Whereas clients, even if they're very long-running jobs, they could even be MPI jobs, they could run for quite some time. By comparison, this is a short duration compared to the service. And the servers are going to dedicate communication resources for those peers. For example, the clients that connect to them. So they could do memory registrations. They will have address vector table entries added. So these resources need to be cleaned up on client disconnect. And this can become harder if the client does something unpredictable, like a crash. So we could have an abrupt disconnection rather than an orderly one. So this is harder to get right. We have seen issues where we might have 2 independent client executions from the same client machine end up reusing the same client address. And so there's been some difficulty in some cases differentiating between the 2 independent client runs. In terms of the MPI model, all processes typically launch together, compute together with communication, and then exit roughly together. You might be tempted to say, well, the DAOS servers could be considered an MPI application of sorts, but as I explained earlier, they operate in an inherently dynamic environment where the server group will contract and expand due to faults or administrator actions. The third main bullet is about multi-threading, and it's not about multi-threading in general. It's more that DAOS has a number of different activities that happen within those threads, and so it feels like maybe the kind of workload that it may present to the fabric might be just a little bit more diverse than what an MPI library might be doing with regard to fabric communication. And the fourth bullet is about so-called multi-tenancy. It's really multi-tenancy with respect to the fabric. So if we just had one client application on the compute node cluster and then the DAOS service, to the fabric, this is really 2 tenants. And so some providers may not easily accommodate this kind of model as compared to, for example, one user launching a big MPI application across everything. Okay, next slide. This slide is focused on scalability, issues that we have observed while scaling up clients and DAOS servers. On the previous slide, we talked about some of the server resources that are created for clients, like memory registrations, buffer allocations, AV table entries. So this just becomes, ever more important with scale to make sure that these resources are handled appropriately. So we've seen some AV table entries left behind, memory registrations, etc. We also talked about multi-threading on the last slide. Here, this is more multi-threading in the general sense. This is sort of generally difficult to get right in software. And so we've certainly seen in some testing, some race conditions happen when running with certain providers. Not too surprising. The memory registration cache itself, we've been turning that on and off on occasion when seeing some buffer corruptions as a diagnosis tool. And so we're kind of looking at whether or not there may be some issues in the memory registration cache as a result of that, that testing. Okay. The second and third bullets, the connection-oriented provider item is really just saying that the address vector table is a fixed size precious resource. And so we need a solution for evicting stale or older entries so that we can make room for example, other clients that may appear and that the servers need to interact with. And so because of the scaling considerations with some of these resources. The RxD connectionless provider was looked at, but for performance reasons, RDMA services are necessary to get high performance in DAOS. Okay, next slide. I think we're running a little short on time. This is less important a slide, but basically this is focused on provider robustness, and it gives an example of DAOS looking to migrate from using sockets in some cases to the RxM TCP provider. And then the others are just sort of wish list items for testing at the lower OFI LIBFABRIC level that might emulate the ways that DAOS presents workload to the fabric. Let's go next by 2 slides. So this slide is talking about some potential areas where DAOS could potentially consider using network or fabric features. So the first item really just refers to some challenges on the client side. We just saw a talk about multi-rail exploitation. So each environment, whether it's MPI or Lustre, has to solve the problem independently. So the suggestion here is maybe a solution could be developed at the OFI LIBFABRIC level to present some sort of virtual single interface. And so that's the basic idea there. The second item, we did talk about how DAOS, when it does do RDMA for bulk transfer, that it's server initiated, and that's done for a number of reasons, scalability being one, security controls being another. But in some special configurations, we can imagine maybe there could be some value in client-initiated RDMA to be able to reduce latency. This might be something akin to what the MPI libraries do with eager transfers. So the third item is talking a little bit about that rebuild procedure and the idea that it's throttled compared to client I/O to not interfere too much with the ongoing most important priority. And so
I have
that's
10 more
done.
minutes, okay? I'll come.
Okay.
Okay, good break.
Yeah, this will be my last content slide, and then we can go right to Q&A. So the idea here, rather than using thread scheduling mechanisms to regulate how much the rebuild takes compared to client I/O, to try to use potentially some traffic management features, for example, in switches. And then the telemetry item is just basically recognizing that some of the emerging capabilities, for example, in switches for in-band telemetry may help identify the cause of intermittent performance issues on any kind of running service, and the DAOS storage service would certainly stand to benefit from getting that kind of insight. Okay, so why don't we jump ahead to the last slide, which is just pointers to the DAOS source code on GitHub and the documentation and some information about our community mailing list. So with that, we can go, I guess, to Q&A, and certainly thank you very much for the chance to present.
Thank you. Sorry, earlier I realized I was not unmuted. Anyhow, I am going to unmute Joanne and Alex in case they like to add some thoughts, remarks. So here they are. We do have some questions coming in. The first one is around RPC based. So since this is RPC based, is there a separate thread or threads to do marshalling and unmarshalling of RPC messages?
So I think there are multiple communication contexts, and so there's multi-threading at that level, but I don't believe there are additional threads specifically for marshalling and unmarshalling.
Correct. Can you hear me?
Yes.
Yes. Hi. This is Alex. Yes, the marshalling and unmarshalling for each RPC happens within the context of the call that performs the RPC. So there is no separate thread that does the marshalling of data.
Okay. Thank you, Alex. And then the next question was for shared in-cast variables. When the data gets updated, does the data get invalidated, and how does the updated data is looked up or served?
So Alex, that's probably a good question for you to answer, being intimately involved in the CART development.
Could you repeat the question so that I get the
Yes.
understanding?
For shared incast variables, when the data gets updated, does the data get invalidated, and how does the updated data is looked up or served?
So whenever there is well, incast variable consists of the three features, so to speak. There's a way to update the data, fetch the data, and validate the data. Usually it's the caller that makes a decision of how the data should be propagated. For example, if a caller is issuing the call to update the data, the caller at the same time can instruct whether to invalidate the old data on all of the nodes or specify, for example, a synchronization parameter as part of the update to how the update should propagate through all of other nodes. The examples would be, for example, there's an eager or a lazy update feature that lets you either synchronously or asynchronously synchronize all of the other nodes on elsewhere. The actual whether to invalidate the data on all other nodes is going to be up to the caller from the perspective of the card or incast variable framework. So it's the ultimately the DAOS based on its algorithms makes the decision how and when the invalidation is going to be done.
Yep. Alex, your voice is coming in and out, so maybe you
Oh,
need to get
I'm
closer
sorry.
to the microphone. We got some parts of it. Let me know if the response need to be repeated in the Q&A window. We'll have Alex answered. I got some bits of it already. The next question here is around DAOS and how it's been tested. The question is, at what level of scale has DAOS has been tested so far? How many servers and what kind of throughput has been measured?
So I'm not as familiar with the specific scaling degree and performance. Johan, you may be able to better speak to that. What I can say is there's been a recent IO 500 run, and I'm not sure if, let me see in the background slides. So there is some information on the IO 500 benchmarks testbed. So here we had either 10 or 26 compute nodes. And in the 10 node case, we had 31 client ranks per node. For the 26 node scenario, we had 28 ranks per node. And then on the server side, we had 24 storage nodes. So that's one example of what was used for the IO 500 benchmark runs that was presented at Supercomputing 19.
Good. All right. We do have one last question here. Any performance numbers with respect to read objects per second per core?
I'm sorry, I missed the question.
Any performance numbers like read-write objects per second per core?
I don't know those numbers off the top of my head, unfortunately.
Yep. Okay.
So Johan is, I think Johan's having some technical difficulties, so he's
okay?
typing at me. So
All right,
up
Johan, let me
to,
see if you are not unmuted. You should be able to talk technically. Let's see, try it out. Nope, we cannot hear you. So yes, there is technical difficulty here.
right, so his answer on scale, so tested on the Frontera supercomputer with hundreds of clients and servers, and up to 8 GB per second per core of bandwidth.
Okay. That was the last question for you I had today. We are also over time by a couple of minutes. Still okay. Any other final questions, thoughts for that we can be answered in 1 minute maybe? All right. So with that,